the three-phase transformer. And so why do we need three-phase transformer? Because we need high power. And we need the high power, you got to have bigger transformer, so it's not economical to have just one single phase. And the old transmission line, substation, station, we are already using wire system, three-phase system. So we got to have three-phase transformer because we have a three-phase system from the beginning. And using a three-phase transformer has many advantages, like it's lower cost and less weight using than three. But why do we need three-phase transformer? If you look for the power station, when they start generating power till it will be at the customer end, that's simply the power system in general. You have the power generation station, and could be any type. Could be steam turbine that use it, or nuclear reactor. Anything, just when I use it to boil the water and then just get the steam, and the steam start to rotate the turbine, and the turbine it's coupled to a generator, and usually most of the time, all the time, we are using synchronous generator, and that's why we're going to study also the semester synchronous generator. So the generator hooked to or coupled to the shaft of the turbine that's rotating by the power of the steam that's generated by whatever kind of energy. And so the synchronous generator will convert the mechanical energy into electric energy, and you get big power. But it's going to be transmitted through transmission line and for long distance, far away, because usually the power station is important in a place where the houses and everything, because they're very polluted. And then what they do far away, always in remote area, and then they want to transmit the power to everywhere. So they use transmission line for long distance, and that will cause power loss. You have a wire, you have a cable, and then it's like running for like thousands of miles, then the power loss will be high. So what should they do to minimize the loss? High voltage, that's right. Why high voltage minimize the loss? Well, that's almost the same, because when you look for the power loss, it's proportional to the voltage square. So every time you increase the voltage, then you decrease the power loss through the transmission line. And then how you do that? If let's say the generator like generating 380 voltage, and then you want to make it 11 or 33 or 15 kilovolt. 22,000 volt, 33,000 volt. We're talking about high voltage. Who's going to do that? Transformer. Imagine the size of the transformer is going to step up this voltage. Huge. And I can show you a picture. That's at the transformer using the power station. And it's not just cooled by air. Oh no, there is oil. It's like a car. It's huge. Imagine all this voltage and the power transmitted everywhere. Then, after that, it's going to the customer. You cannot just give the customer or the houses are getting like 11 kilovolt. That's very dangerous, and you don't use it. You use 110 or 208 if you got three phase. So you get step down transformer. So that's the step down transformer. All these transformers are three phase. Okay. And customer, and we have the step down transformer. We call it like a distribution transformer. So there is step down from the substation. All right. The power generation in the main station. Usually there is a step up three-phase transformer, step the voltage from 380 up to 33 kilovolt. Distribution system, then it will be go down. Actually, distribution transformer, we got two types. They can use single phase and they can use three phase. That's here the three phase. I'm sure this one is like single phase transformer center tap. So that's the transformer, and then it will have like three wire, or we can say two wires and neutral, and that's usually inside the house. You'll find that we have three phases here, and that's three phase system. We got A, B, C, neutral. We got three phase system. So distribution transformer could be three phase transformer, could be single phase transformer with center tap. So this one 120 to 40. So it means you can get 120, get 120, or 240 if you have something like dryer, something like needle. So you hook it to the 240 voltage. Because 110 will not be enough for it. It needs high power, always a dryer, because it needs heat. It's going to produce heat. So that's one picture of the three-phase transformer distribution is also used. Yeah, the output is low, but still, it's not like at the power station, because when it gives it down, the power station is just power station, huge transformer. After the voltage line at the end, and once divided, you have inside our house there. Also, still be used oil for cooling and air and other things. That's one example of distribution transformer, and that's one from the substation. Okay, so how we do three-phase transformer? We already did study the single phase. So we can get like three single phase transformers and then be connected as three phase. So you have here single phase, phase A, phase B, phase C, and then you start to connect the end of the primary. That's the primary, and that's the second. That's the primary of phase A. That's phase B, primary, second, and so on. Phase C, primary, second. So you have three winding for the primary, three winding for second, but estimated. Or the more like here. It's only one transformer. And then in each core, you have two windings. The top, the primary, and the bottom one, the second. The same thing. So that represents phase A, phase B, phase C. So we got two options. So either we have three single phase transformers or one three-phase transformer. And both transformer, single phase or three phase, there are two types of the structure of it. The first one called core type. So if you look for the core type, that's single phase. You have this rectangular one. You have primary winding on one side, secondary winding on the other side. The same thing if you go, that's core type. And the core type three phase, the same thing. But as you know, you will have the primary and the secondary here. Maybe you cannot distinguish. Sometimes you have the primary in the top, and the one in the bottom, but they prefer secondary and the primary on the top of each other, because we'll be linking flux when we go from the primary, we'll be linking all the one with the secondary, be more efficient. So you have here phase A, you have phase B, phase C, but that's in the end, that's called core type. There is another type called shell type. Shell type, they put it in the middle here. You have the primary and the secondary, and that's the flux will be going in this direction. And the same thing here will be for the three phase. You have primary and secondary for phase A, for phase B, for phase C. And there are advantage and disadvantage of each one. If that's as a like structure, but both they do the same job. You can step up, step down, everything. If we summarized here, I'm just showing you the schematic diagram so we know that's the core type for single phase, and that's the shell type for single phase. So obviously you have the primary and the secondary, that's in the shell type on one limb, on one core, and this one will be in two different limbs here. What the difference? This one require more cover than this one. What kind of cover I'm talking about? The windings. Because here the magnetic flux is linking everything, the leakage is like minimum, so you don't have to have copper winding more than what we use in core type. This one used for high voltage, and this one, the shell used for low voltage and medium voltage. Do you prefer this for high voltage and this one for less than high voltage? That one doesn't need more insulation. This one needs more insulation. The output power is low, the output power is high. The loss here more than, because obviously when you have the flux here linking and the leakage is minimum, so you can save power. So it's more efficient. Plus something that maybe when you study power you will learn about, is something called third harmonic. Third harmonic, if you study for your series in signal processing, any voltage can be decomposed into series of sinusoidal with different amplitude, different frequencies. And this happens when you have distortion in the sine wave, distortion in the waveform. If you don't have smooth sinusoidal, and that's very inevitable, it happens all the time, that you will have distortion in the voltage, because the load that we use usually is not linear load, non-linear load. We have electronics, we have many things. So you'll find that the waveform is not really smooth sinusoidal. Maybe you have notches here or like that because of the non-linear load. This causes harmonic. So one of the terrible harmonic, third harmonic, third frequency of this component 3 times the fundamental component. I'm talking about frequency. The amplitude is less, but the frequency 3 times the frequency of the fundamental component. This one can alleviate it because when it go when we use the 3-phase, then that will go in this direction, and this will go in this direction, the flux, and this one will the same in the opposite. Then they cancel each other. So this one will alleviate the third harmonic. So that's one of the advantages. Anyway, there are a lot of things we can talk about the transformer. There are many things in it, but just let's say now continue how you connect the windings of the transformer. It's, you see here, it's free. You have the primary, you have 1, 2, 3, you have 3 primary windings, you have 3 secondary windings. You are free to whatever the connection you need for your application. You might make it YY, Y delta, delta Y. Well, let's just look how we connect. Let's say that I want to connect this transformer in front of me. Well, this transformer is 3 single phase transformers. I have 3 transformers in this way. Remember, the primary and the secondary. Let's say that the primary, I'm going to apply the source, and the secondary, I'm going to connect the loads. So usually the current will come from the supply, will be in. So I want to remember this. The current will be in the dot, and then inside the transformer, out the dot like that. That's, I'm going to connect the load. So usually the current will come out. So if you continue, you'll find that inside the winding, the current is in the dot and is out of the dot. Nobody asks. Just don't take anything. Anybody tells you something, you take it. It's okay in the dot. What is the dot? Yeah, there's a polarity, but how do you know the polarity? What? When you find transformer, will you tell you where is the dot? The dot, this dot in the transformer, what does it mean? And physically, can you see the transformer? That's true, it can define the polarity. That's true. We want to know why, how, and physically, can you see in the transformer dot, like here, or just that's what assumed? And what does it mean, the dot, and why changing the polarity? For a simple reason. If you have a core or iron rod like that, and then you have the winding like that, and you can do that like this. And I'm going to show you, I'm not going to change the current direction. So from the top of the rod iron like that, so the flux will be in this direction, right? Because if you make your thumb like that in your right hand with the direction of the current of the coil, so your thumb will be the direction of the flux, and the current here in the same direction, but the winding is behind the core itself. So the coil current direction changed now. It's not, so the flux will be down because it's connected to the secondary. They are linking the secondary winding. And according to the flux direction linking to the secondary winding, you will have the voltage positive or negative. So when you make the dot like that, physically you find mark on the transformer. Here, this is the dot, this is the dot. It means when this one is positive, this one is positive. When you have voltage positive in this, so if you have the voltage like that, whatever step up, step down will be in phase. But if you have the dot on the bottom, you will find the voltage like that, flip. So that's the importance of the dot. Yeah, maybe it will not get problem yet, but just you got to know it. So when you will work in any company and you're clear about the dot, it's a very simple thing. But in industry, few things like this is very effective. You take it seriously. So now I wanna see how I connect this one delta Y delta, 3 single phase transformer. So I will connect it delta Y. So you focus with me on that because you should understand how you connect. That's the primary, and any winding has like the beginning and the end. So this is like the beginning and this is the end. One terminal and second terminal. So to do the delta connection, if you remember, you did in the lab, three-phase, you connect delta like you connected the end of the winding to the beginning of the second one or the following one. So that's what I'm going to do. Let me just do it in red. So that's the end will be connected to the beginning of the second one. Because always we assume the top is the beginning, and then the end of this one to the beginning, and this one is the end to the beginning of the top one. Where is the input? The input still goes in A, B, C. So I have a wire at A. That's the A. I have a wire. Make sure it didn't touch it. B. Oh, I'm sorry. That's oh. I have one here from B and one for C. So that's how I connect delta. Let me show you here in the other, because you might face two different type of graphs. That's A, and that's B, and that's C, and that's the beginning of each and the end. That's the dot. So the end of this one will go to the beginning of the second, the end of one second, the end of this one to the beginning of the second. That's delta. All right. Now let's go for the secondary, and let's just agree together that that I'm going to use the letter the uppercase for primary and the lowercase for second. So capital A will be for the primary and small a for the secondary. Now I want to connect this star, but you got to remember the dot here. It's towards the terminals of the out. The dot here towards the terminals of the input. And something else, the current, as we agree, it will be in the dot at the source. If you remember when I explained refresh your memory, that's the transformer. And that's the primary. We assume that the input coming from there. So the current coming here, okay. So to be in this direction. So that's not right. So according to the single phase, that it's in from here. That's right. That's a dot, and the current going in, so it'll be like that. All right. That's very important to affect our analysis. Currents coming from the source, and that's the output. And we said that the output like that, if you connect load, will be going like that. So it's in the dot. So here you go, in the dot. That's very important. And then you are going to connect it as a star. And star is easy, just connect the all terminals by one wire and make it the neutral. So that's easy. You connect this by this, and we did that in lab. You are familiar with this connection. So what I have here, delta star. All right. Delta. I just show you delta star because it has two different type of connection, but you can do that primary or second. But observe, I know you will know how to do the connection, it's easy, but the thing that I want you stress on the direction of current, the polarity of voltage, because it will affect the analysis. So the current of the primary coming out of the dot and for the output in the dot and parallel. Another thing, remember, this transformer. It means every single transformer on one coil. What does it mean? It means if the current going here in this coil and current going there, yes, there will be a ratio. Someone is smaller or bigger number one, but they are in phase. It means if this current on angle 0, this current on angle 0. This current on angle 30, that will be 30, because they are in the same coil. They are in the same coil, the same flux linking them. So the current will be in phase. Okay. Here, the current going in this coil. Very important. So if you call this IAB, why I call this IB in delta? Because the current comes from A and going to B. And that's what I call it IA, current in phase A. So IA and IAB, they are parallel, they are in phase. So I make it like that. Different in magnitude, but they are in phase. So that's factor. Well, let's continue. Well, here I'm showing you what I did. One star, one delta. It's very easy that the way we do it. And this is another way that we get familiar with it more than that. But this is actually what we do in the lab. That's what we do just to make it look like delta and help in other analysis too. So there are many kinds. You can have star delta, star, whatever. But you got to know that we be involved in the relationship between phase and line for delta and star. And just simply, as we studied in three phase, that's why we review three phase circuits. In a star, if you look at the star here, the line voltage or the voltage from line to line, it's bigger than the phase, right? By square root of 3. And the current of the phase equal the current in the line. Delta the opposite. The voltage between line and line, like this one, between this line and so it's the same as on the phase. So line voltage is equal phase voltage in delta, but the current is bigger than the phase because there are two currents involved, will be square root of 3. And of course, there is the difference of the angle 30 degrees, plus or minus we discussed before. So keep this in mind. All this information will help us to analyze the transformer. Remember that the turns ratio for single phase transformer, it's N1 over N2, or the phase voltage 1 or phase voltage 2, and you can say also equal the current of phase 2 divided by phase 1. We are familiar with this. This is the turn ratio of single phase, not three phase, single phase. Well, what happened to the turns ratio for three phase? This example. Right, transformer. I just write like X, F, and R. That's transformer, right? So that three-phase transformer is assembled by connecting 3 and 360, 120 voltage. Transformer each. And the primary 360 and the secondary 120. The question now, what is the rated value of the power of this transformer as three phase when I connect them, whatever the connection? Delta, huh? Not the same. You got 3 of them. A 3 transformer. If I said that you have 3 transformer, each get 300. So the first thing we do, you find the rated value of the three-phase transformer assembled by three single-phase transformers. Say the power of three-phase transformer is equal to 3 times the power of one phase, because you are adding them. So 3 times it's 720. What to get? 1,160. And you can convert it to kilo volt. So that's the power of the transformer. Great. Which one we call the turns ratio A, and A is equal the voltage of one phase. It is just right, one phase. Voltage of one phase Oh, I write this right because we have two sides. So the voltage, that's phase, and 1 for the secondary by 2. Can you write like that? Yes, phase 1 over phase 2. Or you can write it I, phase 2 over I. They are opposite, the voltage and current. In this case, what is the voltage at the primary for the single phase? I'm talking about single phase. 360, right? Be 360. Okay, 360. Divided by the voltage of the secondary. The secondary winding rated value 120. So divided by 120. So what is the result? 3. So each transformer has turns ratio equal to 3. The primary 360, and that's 120. And the rated value of each one is 720. So I'm making 3 of them like that. So that's the turns ratio of what? Single transformer. So let me write that. A is the turns ratio of a single phase transformer. This turns ratio, we are going to call it A dash. That's turns ratio of three-phase transformer. How we'll do it? The same definition, but instead of using phase, using line. So you say A dash to the voltage line of the primary or line voltage of that second. That's the definition. It should be equal to also the line. It'll be the same. So just look for the voltage anyway, but I want to make sure that you understand that. How can you get it from this part? Just use this part to get A dash. Well, it's easy. I will say A dash equal to the line voltage, but you have to know now the connection, delta or Y. We have to go for the problem here. They said that they are going to connect it to delta Y. Delta Y. So what does it mean? It means the transformer will be like that, delta Y. And we can make like small sketch just to remember what we are doing. Delta Y. Remember, the phase, that's the phase. When you connect in, what is the phase? I'll just make it a little bit box, dark box here. That's the phase, one transformer. What is the phase here? That's the phase. So the phase voltage here, according to the single phase, 360. And the phase in this side, in the second side, 120. Now I'm connecting them. The first one, or the primary, as a delta, and the secondary as star. The question now, what is the line voltage at the primary? What is the line voltage of the primary? This is the line voltage between this line and this line. So what is the value of the line voltage at primary? The same, right? Because between line and line, the same as its phase. So B 360. So I will say that this value is equal to 360. All right. Now go for the second. This is side one. This is side two. That's from line to line. And that's the phase, one phase. One phase, one single phase transformer. Because remember, there are three single phase transformers. So when you connect in this way as a star, so between one line and the second line, what is the voltage here, line two? Square root of 3 times the one phase, right? So that will be VL2. You will have 120 here. So be 120 times square root of 3. So I'd like to write it in general way because this is specific, but I'll say A dash is equal line voltage over line voltage in the secondary. Since this one connect delta, so VL1 is equal the same as phase 1. The line voltage 2, it's equal square root of 3 times the phase voltage. Now, you can write like that. The voltage of phase 1 divided by voltage 2 divided by square root of 3. What is the ratio between voltage phase 1 and voltage phase 2? We call it the name, we give it a name. Is the voltage phase 1 over voltage phase 2, right? So it's equal to A divided by square root of 3. We got good result. A dash is equal A by 3. So when you have a transformer connected, delta Y, so, and you know the turns ratio of each one? So line to line, or the turns ratio for this transformer as three phase is equal A divided by square root of 2. What does it mean? It means that any voltage in the secondary node between line and line multiplied by A dash, you get the voltage of the primary side. And the current vice versa will be like that. So we got the turns ratio of the transformer, this type delta Y. Question is always A dash equal A over root 3 for a three-phase transformer? No, it's only for this case I'm discussing. For delta Y. If you make Y delta will be different. Y will be different. Delta will be different. I'm just showing you example, but you got to check yourself when you go home. Can you get it? I'll give you the table. Can you prove it, each one? Or at least a couple of them, so you know they understand it. So that's how you get the turns ratio. What is the transformer? And the parameters are given. What do you want to do with the transformer? You want to do analysis. On the secondary side, you want to know what is the voltage and the current of the primary side. That's the application you're going to use usually. You're going to analyze a three-phase transformer. And it's very important to know the current, to know the voltage. Why? So if it's designed or you want to choose, let's say I'm not going to design transformer, I'm going to pick transformer from the market. I'm an engineer and they ask me, okay, buy a three-phase transformer for this application. It's not enough just to say, okay, what's the voltage that you want? We need this. And we have here 1200 volts. One 400, 1200 volts. That's not enough. What about the power? You'll find many transformers 400, 1200 volts. There is one 100 volt AM. There is one 1000 VM, or there's one 2 kilo AM. So there are many. Which one are going to use? So you have to do the analysis to do the current and the power. So how can you analyze three-phase transformer? No, they do it equivalent, like you did exactly in single-phase transformer. Find the equivalent circuit. But to find the equivalent circuit, the values will change, depends on the connection. Very involved. As to solve three-phase transformer, you got to have clear mind. sleeping well, relaxed. So he can, because if you miss something, you miss square root of 3, 30 degree, it's math. And you're not dealing with small power, as you see, you're dealing with kilo or mega vortex. How can you find the circuit? Well, let me just show you the circuit in the end, what to look like, and then we'll check together how we reach this result. In the end will be a very simple that's what I get. You have the second V2. Yeah. The reactance of the primary, and you got the branch for the and yeah, I know it's in the beginning you can make like simple calculation. Cannot get equivalent per phase circuit for a three-phase transformer except if both are Y connected. Because if you have Y connection, you take only one phase with the neutron. That's what it is. That's what they do. So you don't have problem if you have Y connection. The problem only occur when you have delta connection. How you solve this dilemma? Easy. Delta dealing with balance. Balance by 1/3. That's the current Y. That's number one. So, and then you get the equivalent. So simply find the equivalent Y for that. And that's why in this example, intentionally I got delta Y. So you can have both. Well, so how we start to find the equivalent circuit for this delta Y? We found A, we found A dash. Let me sketch for you the, let me sketch, I have only 2 minutes. I will just do the starting and continue next time. If you sketch the connection of the transformer as we did, that's A, B, C, and you have on the other side A, B, C. And the dots as we're here. We said that the current going in this direction, and we said that the current in this direction, and we said the connection is Y, and okay. When you make it like that, it means that if this A linked with this small a in the same core, so they should be parallel. So what does it mean? If you are working about the sequence, that's IAB in the primary, and then you have IBC, and then have ICA. That's in the prime. So when you sketch for the phasor diagram for the secondary, what you'll do, IAB, that's IAB, is linked with what? IA. So when you do the IA, you do it parallel. That's IA, that's IB, and that's IC. So IA connected with IAB. What does it mean? They are in phase. They are different magnitude. And the ratio between them, it depends on A dash. But they are linked, they are in parallel. So that's the first thing that I want to do. And next time I'll continue.